the Iod506 video in superlab. In this lab, we're going to be looking over the skill sheet that's called Analyzing Given Information when presented with new simple information. Before you get started, you should make sure that you have the skill sheet in front of you. Also, please make sure that it's the new version of the skill sheet, not the original version of the skill sheet. You can tell it's the new version because if you flip it over and take a look at the first question on the back, that's a self-practice question. It should say a light of wavelength 0.55 microliters is shown on IO. According to figure 2, what is the reflectance you should expect? If it says according to figure 1 on your sheet, you have the old version. If you have the old version, you want to make sure that you acquire the new version. Right? If you don't have the new version, you should get it right now. All right, so with that new sheet in hand, we are ready to get started. We're going to first go through the background information to learn a little bit about what the skill Iod506 is. So I have a volunteer to read the background information for us. Thank you, ma'am.
Any skills on the ACT require that you take some sort of information given and use it to make English conclusions. Iod506 is an example of this type of skill. For Iod506, you will first need to examine the table, graph, or diagram given in the passage. You will then be given some new information. The test question will ask to make a conclusion based on combining the original data from the passage with new data presented in the course. Excellent.
And you'll always be able to recognize these because it'll say something like, a new study was done and they found blah, blah, blah. Or a second set of data was collected and they found blah, blah, blah. All right, those are the kind of questions that are especially typical of Iod506. All right, let's take a look at the passage. What we see up here first is the background information. As we read through the passage, a great strategy that you should get in the habit of is circling, highlighting, underlining, however you need to, make a little check mark next to any words that you find confusing or tricky that we can then go back and find later on. We don't want the vocabulary to get in our way. All right, so in your hand right now, you should have some sort of writing implement ready to circle, highlight, or underline words as our reader reads for us. We have a volunteer for someone to read the first paragraph on this passage. All right, so let's take a look at the background passage.
Other images of the surface of Io, one of Jupiter's moons show plumes of gas that resemble Earth, geysers, and active volcanoes that expose a molten material. The material descended from Io's volcano from plumes that produce solidify at Io's cold surface fissures. Scientists believe that these materials may be one of several allotropes of sulfur or sulfur compounds. The following studies were performed to determine the composition of these materials.
Excellent. So let's take a look at anything that is circled or underlined from that reading. Did anybody have any words that jumped out at them that we should go over before we go on?
Geysers.
Geysers. Nice. Any other words? Plumes. Excellent. Any other words? Molten. Definitely one that's a new word for us that we read before.
Allotropes.
Allotropes. Good. Any other ones? All right, as usual, there's 3 different ways in order to learn new words in science, especially on a passage like this. They're either defined for you, you can use background knowledge or context clues, and the third way is to look it up. The ACT, we can't look it up, so let's try to figure out from one of the first 2. First off, show plumes of gas. Anyone think of what the word plume would mean if we're talking about stuff coming out of a volcano, gas coming out of a volcano? What's a plume? Yeah, it's essentially like that big chunk of gas cloud. If you're looking at a volcano, and you know how you see like that thing? All right, this is the plume. All right, that big gas cloud that shoots out of the top of it is the plume of the volcano. All right, what about geysers? Has anyone ever heard the word geyser before? What do you think geysers do?
I think it's that thing in like that hole in the ground and then it shoots up like air, gas, or something.
Yeah, and also the way geysers are a little bit different than volcanoes is they also shoot up a lot of water. So any liquid that's below the surface. So if you ever heard of like Old Faithful? All right, Old Faithful, the geyser, essentially another hole in the ground, but this hole in the ground shoots out water. All right. Molten. This is a term that we use a few times, especially for those who just finished the review guide. What does the term molten mean? It's often used in terms of like lava. What does molten lava mean?
Would it be liquid or something?
Yeah, it's liquid. It's the liquid version of something, specifically being melted to become a liquid. What do you mean by molten? And then last but not allotropes. Allotropes is actually defined for us in the passage. All right, what does this word allotropes mean? Forms, yeah, it's different types of. All right, so you see right here, it's some forms. So when it says maybe one of several allotropes of sulfur, it's just one of several different forms of sulfur. And as we'll see, they usually classify them based on color. There's brown sulfur and red sulfur and orange sulfur. All right, let's take a look at the experiments and what they did. Do we have a volunteer to read study 1 for us? Thank you.
Reflectances were measured at a visible light wavelength between 0.5 micrometer and 0.20 micrometer. Everyone showed when they looked for the various ions hold this reflectance for the reflectance of ions prior physical surface measured all at once was measured at 2 different times. Surface. Figure 2 shows the data on the reflectance data calculated to create their model. This model shows a combination of materials in figure 1 will produce the closest match to the measured reflectance data compared to the model. The overall composition of ion surface index 15% SO2, 50% orange dust, 20% yellow, and 15% white dust.
Fantastic. All right, that one was a long one. Are there any words that we want to go through from that? All right, to highlight the vocabulary. All right, we definitely want to make sure we understand this word reflectance right here. This is going to become incredibly important for the rest of this passage, this word reflectance. Any other words in here? Going once? Going twice? All right, so when we say reflectance, what do we mean by reflectance? It's sort of defined for us in the passage there. All right, what do we mean by the word reflectance, especially the term reflectance? What does it say it is in the passage?
Refraction of light striking a surface as reflected by light.
All right, so if something has a high reflectance, what does that mean about it? I said like that object has a really high reflectance. What would that mean?
Would it be that it's exposing lots of light?
Yeah, it reflects a lot of the light that hits it. All right, so can anyone think of a type of material that's got a very high reflectance? A mirror is probably perfect. It's almost perfect reflectance. All right. What about something that has really low reflectance? Anyone think of an object that when you look at it, it actually doesn't reflect a lot of the light? Yeah, the tables could definitely do that. The wood on the tables, wood is a very low reflectance. It doesn't bounce back a ton of the light. It keeps a lot of the light inside. Good. All right, and so what we're going to see is that the light is actually going to be measured in percentages that are converted into decimals. So if we examine these two data representations that go along with the passage, we're looking at both figure 1 and figure 2. All right. In figure 1, what do we see being measured here in figure 1? Like if we were going to halt this, what are the axis labels here that they're comparing?
Wavelength and reflectance of all the colors.
Perfect, yeah, wavelength and reflectance. So essentially light can come in different wavelengths. As you change the wavelength, you actually change the color of the light. All right, so if you guys have ever heard of like rainbows are Roy G. Biv, if you've ever studied that before. All right, we have very, very low or very, very long wavelength lights to very, very short wavelength light. And so as you change the wavelength, you can actually make a different color. So the only difference between red light and green light is the wavelength of that light. All right. And so what we see for different wavelengths then, if you shine it on a particular type of sulfur, how much light is reflected? Right, that's what we're seeing. So if I ask you a question like white S, so for white sulfur, does it reflect more high wavelength light, or does it reflect more low wavelength light?
High.
How'd you get high?
I looked at the graph and the top, the highest one and low.
Yeah, all right. If you look for white S, that's this line right here, and you'll notice the reflectance is way higher up here, which is for this 0.6 microliter light, and it's way low down here when we're talking about like 0.35 microliter. All right, so for white S, the higher the wavelength, the more it reflects. All right, now you can see the same kind of thing here happening for Io. When they say the whole disk reflectance, what they're looking at is the entire planet. All right, so if you looked at the whole planet, you shine different light at it, how much would bounce back? All right, and then let's take a look at study 2. Can we have a volunteer to read study 2 for us?
At two different times, reflectance were measured of the crater floors of two volcanoes on Io, Heli, and Sirte, figure 3. Should the reflectance data.
Excellent. All right, so we see it right here. We see the Sirte crater, and we see the Pele crater. All right, now one thing just to clarify too about these figures, so there's essentially 4 graphs total. There's all in figure 3, which is both of these 2 graphs together in one. Then we have figure 2, which is this one. And then we have figure 1 right here. One of these graphs, the data in it was not taken from space. For which one of these graphs did the data not come from somewhere in outer space?
Figure 1.
How'd you get that?
Because the title says laboratory data.
Yeah, this is laboratory data. So essentially what they're looking at here is real samples of this stuff that we already know. Because what they're going to end up doing later is trying to figure out what Io is actually made of based on other known values. All right, so like if we can take a look and we know that it's not listed up here. Let's say green S has a curve that looks like that. And then we were to look at a planet and we say, hey, look, when we shine light on it from different wavelengths, it looks like that. We'd be able to say, hey, well, that planet is probably made out of green S then, because it has the same reflectance that green S does in a laboratory. And so that's what they did here. They found a whole bunch of known ones to say, all right, well, when we actually shine it on these other ones, we can figure out what it looks like based on its reflectance. All right, that's kind of the whole purpose of this experiment. So let's take a look at the example question. A rock was found on Mars that reflected 20% of the 50 microliter light shown upon it. All right, this is an Iod506 question. So here's our new information right here. Based on the data in figure 1, what allotrope of sulfur is it most likely composed of? All right, so we need to use our new information about this rock found on Mars, combine it with the information we already know in figure 1 in order to get the answer. All right, how would we get this answer? First off, what is the answer here? What allotrope of sulfur is it?
Is it red S?
It's red S. Yep, good. All right, the answer is red S. How did you get it?
I just looked at 50
Micrometers.
micrometers, and I looked at the bottom where it says wavelength. So I looked at 50, and then I looked at 20%, and I just connected the lines.
So this line would go, oh, geez, that's not very tall. And this line would kind of go like this. And we see that they actually intersect about right here, which would be on red S. All right. What you want to do now, if you are watching the video at home on your own, or if you're in the classroom right now with your teams, are answer questions 1, 2, and 3. Essentially, this is going to give you some background information on what the graphs are showing, So you're just looking for the different variables that are being listed in these graphs. When you are ready and you've answered questions 1, 2, and 3, and you want to listen to the answers, press play. You should press pause now. All right, if you are pressing play at this point, that means you've answered questions 1, 2, and 3 already and are ready to go through the answers. As we take a look at question 1, it asks what 6 variables are being compared in figure 1. And 2 of the 6 are given as examples. So remember, there's a couple of things that we're looking at here. The variable of wavelength is what we're actually controlling in this experiment. Right? It's on the x-axis. All right, so in this experiment, we're changing the wavelength, and then we're measuring different reflectances. All right, now we're measuring different reflectances of a whole bunch of things. All right, so we have wavelength. Now, from wavelength, we measured the orange S reflectance on this line right here. We also measured the white S reflectance. We also measured the brown S reflectance at different wavelengths. We also measured the red S reflectance at different wavelengths. And last but not least, we also measured the reflectance of SO2 . Okay, let's use the same idea and start to take a look at the next figure. Sorry, this one's a little bit blurry. Some of them came out better than others. What 4 variables are being compared in figure 2? You have a volunteer to answer this one for us? Again. All right, so we have the reflectance of 2, which is already given for us in here. We also have, you said, IO observation 1 reflectance. What else do you measure? The computer model reflectance. Last but not least, what else did they use? Nice, they changed the wavelength again. Perfect, so we can see for different wavelengths, what was the reflectance of IO observation 1, IO observation 2, and then a computer model simulation of IO. All right, which brings us to question 3 then. According to figure 1, what was the reflectance of white S at a wavelength of 0.5 micrometers? All right, what do we get for an answer for this one? The hint is find the white S line in figure 1, look for the reflectance that corresponds to a wavelength of 0.5. What do you get? At 90%. Now this is interesting. You said 90%, but I don't see percents anywhere on this chart. How did you get 90%?
When you find the reflecting, you look for a percentage and not really a difference. Even though it's not given, it's just, that's how you say it.
Excellent. So if we start, we find 0.5 micrometer wavelength of white S. Hits white S here. We notice it hits about right here. So you may have written 0.90. All right, but remember, we need to convert that into a reflectance because it's the amount of light that's reflected. All right, so white S reflects 90% of 0.5 microliter light that's shown up. All right, so that's why you make sure you put these in percentages. Remember to convert decimals into a percentage. If it's 0.90, you just move the decimal points 1, 2 places to the right. So you get 90. Right, if you ever forget how many places to move the decimal, remember a percent sign has 2 circles in it. You should always move the decimal 2 places. Okay. What you want to do right now is answer questions 4 through 8 on your own if you're watching this video at home, or together in your teams if you are sitting here in the classroom. A lot of these questions, remember, are going to give you new information in the question itself and ask you to think about that new information using the old data that's already there. That's what Iod506 is. If you are watching at home, now's a good time to press pause so you are ready to go through the answers. So answer questions 4, 5, 6, 7, and 8, and then press play and be ready to go through the answers. If you are pressing play at this point, that means that you are ready to go through the answers from 4 through 8. Question 4 says a light of wavelength 0.55 micrometers was shown onto iron. According to figure 2, what reflectance would you expect? What was the answer to this question? You want to share their answer? What did you get?
60%.
60%. How'd you get that?
I looked at figure 2, then I put extra gold from 0.55.
Microliters, good.
Then I went up until I reached the line,
Uh-huh.
and then I went across, which got me 0.6, 60%.
Yeah, good. My line is a little bit probably high because I'm trying to write it on a smartboard. But yeah, perfect. All right, and you would draw it. Oh, yeah, that was no. There we go. That's better. All right, about 60%. All right, now a couple things you need to be careful of. You notice that we started right away on the right side, which is down here, because we wanted to start with the micrometers because we were told that. A danger of this problem is that some people start over here at 0.55 and draw it over and draw it down. You want to make sure that you start where you need to on the micrometer side, not on the other side. And then once you get 0.60, you just need to convert it to 60%. All right, let's take a look at the next one. It was originally predicted that the Pele volcano was made of brown S. First off, why was the Pele volcano hypothesized to be made of brown S? What kind of made people think that?
The line was similar.
Excellent. Oh, and I showed it. Oh, I also took Pele. Good. All right, so if we took a look over here, we noticed that the Pele line kind of has this sort of gentle curve to it. All right, if we look back at this, you'll notice that brown S has almost exactly the same curve. It ends at almost exactly the same point and starts at almost exactly the same point. So the original hypothesis was that it was made entirely of brown S because the lines are so similar. However, it was discovered that the reflectance decreased as the wavelength increases. All right. So instead of looking like this, what would that mean? If the reflectance was decreasing as the wavelength increased, what would that line look like? Yeah, it would be a downward line like this. All right. Now, which one of our allotropes do that? None of them. Yeah, there's not a single allotrope in here that does that. All right. So then our answer choice that we're looking for is choice C. All right, if we take a look at question 6. Question 6 says a 0.65 microliter light was shown onto an unlabeled S allotrope sample, and it reflected nearly all of the light. Using the data from experiment 1, which S allotrope was being investigated? So we have this mystery sample, we shine on a light that's 0.65 micrometers, and it reflects nearly all the light. What is it and why?
I got white S.
How'd you get white S?
Because white S is like it's purely at 100.
Yeah, so
100%.
nice, because the reflectance of 1.0 would be equal to almost 100% of the light being reflected, which is nearly all of the light. All right, now how come we are looking at this side instead of, because you'll notice that white S also is down there. Yeah, and we're looking for 0.65 micrometers, which actually would be over there. Ding. Nice one. All right. Question 7. It was discovered that Io is made almost entirely out of one of the S allotropes. All right, that's our new information. Using figures 1 and 2, which allotrope is Io made of? All right, so here's our IO data on this side. We know this is IO's wavelength versus reflectance. And these are the known values we found in the laboratory. So which one of our known values looks the most like IO?
Orange.
Why do you think it's orange? Yeah, this one goes up and then flattens out. We notice orange goes up and flattens out. All right, so in this case, orange is our answer. All right? Again, this is why they did this study right here, is to be able to have a sample to compare to all the time. And then let's take a look at question 8. The first time the data was collected from the Pele volcano, mostly NO2 was released. The second time data was measured, the volcano released mostly CO2. Based on figure 3, which of the following is likely true? And again, we have a whole bunch of new information here. New information about what was spit out the first time. If we look at the graph, we notice that on Pele, so we're looking at this figure, there's 2 different times where they measured data. The solid line was the first time, the dashed line was the second time. All right, now if we compare those 2 lines, which one of those 2 times had a higher reflectance? The first time or the second time? The second time, and you can tell because this is just a little bit higher than the other part right here. So the first time had a higher reflectance than the second time. If the first time released mostly NO2 and the second time released mostly CO2, what could we say about them? What could we say about their reflectance?
CO2 reflects more light than NO2.
Because CO2 was released this time, we know it probably reflects more light than NO2 was released that time. All right, what you want to do right now is just try the last 2 questions on the new set of data. So there's a new set of data on the Loki crater floor. You want to answer questions 9 and 10 based on this data. You should pause the video now, and when you're ready to answer the questions, press play. If you are pressing play at this point, that means you are ready to answer the last 2 questions. So the question 9 says, if the Loki crater was reflecting 50% of the light striking it, what wavelength of light would be shining at? Now you have to be careful here because you notice they're giving you the reflectance and asking you for a wavelength. What'd you get? 0.37 micrometers. All right, because we're starting with 50% reflectance, which would be right here, and going down to get 1, which should be 0.37. All right. The last question, what material is the Loki crater made of? Well, we know what the Loki crater looks like in terms of its reflectance. All right, it increases and then slowly decreases. So which is the only one of our S allotropes that increases and then slowly decreases?
SO2.
SO2. It increases and slowly decreases. So this is what we made of. At this point, if you have gotten all these questions correct, you feel like you are ready to go, it is quiz time. Good luck to you.